Hello everyone, welcome to ashatech.com. Today we discuss the hydrostatic force on a horizontal plane surface submerged in a liquid. Let us consider a horizontal plane surface submerged in a static liquid, and as every point on the surface is at the same distance from the free liquid surface, the pressure force will be equally distributed over the entire surface, and if the plane is at a distance h, pressure P according to the hydrostatics law is equal to rho g h. Now look at this diagram. This is a rectangular plane surface which is at the bottom of this fluid and is at a distance h bar and the h star, because these two distances are equal and they are equal to h, because the center of pressure P and the center of gravity G are all at the same distance from the free liquid surface, and therefore if A is the area of the surface, and G, which is the point of the center of gravity, is at distance h bar from the free surface, it is also equal to h. P, the point of application of the center of pressure, being at a distance h star from the free surface, h star therefore is also equal to h, because we have said all the points on the plane surface are at the same distance from the free liquid surface. The total hydrostatic force will be calculated using F equal to rho g area times h bar. F acts P or G. P is the center of pressure and G the center of gravity. This force acts at a point P or G, which is a distance h bar or star from the surface. This total pressure acts through the center of pressure, which is at the same point with the center of gravity of the plane surface. Let us look at the example. The figure below shows a tank full of water. This is the tank. The upper narrow section is of length 0.4, height 3 meters. It is given that the width of the tank is 2 meters. The bottom section is 4 meters in length. The depth of the wider section is 0.6. Also, the width is taken as 2 meters because it is the same tank. Now find the total pressure at the bottom. At the bottom of the tank. Let us find the total depth of the tank. It will equal the depth of the small section, which is 3 meters, plus the depth of the wider section, which is 0.6, giving you a total of 3.6 meters. Area of the tank at the bottom is equal to length times width. Length is 4, width is 2, giving you 8 meters squared. Therefore, the total pressure force F is calculated from rho GA, whereby h bar is the distance of the center of gravity from the free surface. Force F is equal to therefore 1000, which is the density of water, times 9.81 acceleration due to gravity, times 8, which is the area, times 3.6, which is h bar, which is the distance of the center of gravity from the free surface. Therefore, the total pressure will therefore give you 282.53 kilonewtons. Let us find the weight of the liquid. Weight of the liquid is calculated as mass times acceleration due to gravity, but mass is equal to density times volume. Now, volume of the water in the tank will therefore equal to the volume of the water in the upper smaller section plus the volume of the water in the lower wider section. Therefore this volume will equal to, this is the 2.4 plus this 2.4 times 2, which is 4.8, which gives you 7.2 cubic meters. Therefore weight of the liquid will therefore equal to rho g times 7.2, which is equal to 1000, which is the density of the liquid, times 9.81 times 7.2, and would give you 7.2 10.81 and 20.63 kilo. Comment: we have seen the results obtained in 1 and 2 will represent the hydrostatic paradox, because the hydrostatic paradox tells us that pressure will always be the same as long as the height of the column is the same, irrespective of the shape of the container, and it will therefore be, the pressure will therefore be independent of the amount of the fluid contained in the container. And for that matter, therefore, that's why the pressure is high but the weight of the fluid is less, is small, because we see that pressure is only depending on the height of the fluid column and not the weight of the fluid. This hydrostatic paradox can further be explained in a way that you have different shapes of the container with the same liquid column, H1 is equal to H2 is equal to H3, and therefore giving you the same pressure, which is independent of the shape of the container. That explains the hydrostatic paradox and explains why the pressure in the above computation is greater than, far much greater than, the weight of the fluid in the container.